Hi everyone, my name is Saif. Welcome back to a new video of modeling and simulation of power system components. Today's lecture is about modeling of single-phase, two-winding transformers. A transformer is a static device that transfers electrical power from one circuit to another at the same frequency but often with different voltage levels. Single-phase transformers consist of two windings placed over illuminated silicon steel core. Those two windings called primary and secondary windings. When the primary winding has this number of turns, it's called low voltage winding. Therefore, the secondary winding, which has more number of turns, is called high voltage winding. Once a source supplies a voltage of V1 to the primary, an alternating flux is set up in the magnetic core, which links the primary and secondary windings. Then self-induced EMF in the primary and mutually induced EMF E2 in the secondary are presented. Those two induced EMFs are developed in phase opposition to the supply voltage V1 according to Lenz's law. This figure is taken from reference number 1, and all references cited in this lecture will be presented at the end of the video. In actual transformers, both primary and secondary windings have some self-resistance called R1 and R2. Now the flux that links both windings of the transformer is called mutual flux, while the flux which links only one winding of the transformer is called leakage flux. The primary leakage flux proportional to self-inductance of the primary winding, which produces a leakage reactance, which is X1. Similarly, secondary leakage flux produces secondary reactance X2. Figure 2 shows the equivalent circuit of actual transformer when no load applied to the secondary winding and hence no current flow in the secondary winding, so I2 equals 0. A small amount of current circulates through the primary winding called IO, which is usually between 2 to 10% of the rated I1 current. This current supplies the iron losses, so both hysteresis and eddy current losses, and it's also supply copper losses in the primary windings. This no load current has two components. The first one is in phase to the applied voltage V1 and it's called active or working component. This current supplies the iron losses and the small primary copper losses. And the other component is the imaginary part, which is in quadrature with the applied voltage, and it's called reactive or magnetizing component. This current produces the flux in the core and does not consume any power. Now, in order to mimic the no load losses in the transformer, both resistance and reactance in parallel are presented to meet the no load losses in the transformer. Again, we are using three different approaches to model transformers. In the first approach, we are using transfer function blocks to model the transformer. In the second approach, we are using built-in Simscape blocks, so resistance, inductance, etc., to build a model of a single-phase two-winding transformers. In the third and final approach, we are using the built-in transformer block, trying to validate the first two approaches. Now, in order to model a transformer using transfer function blocks, we have to have the transfer function of a system, and in this case of a transformer. So we're using the same 4 steps we've been adopting in the last 4 videos. So first step is to find the equations which describe the system or the transformer, and then identify system input and output variables. In this case it's the supply voltage and the voltage output at the secondary winding terminals, and then we should take Laplace transform of those equations assuming 0 initial conditions, and then a transfer function of a transformer will be found. As we mentioned earlier, number of turns at the secondary winding presented by N2 over the number of turns of the primary winding, which is N1. It's called the turn ratio or the transformation ratio, which is K. We already presented the primary impedance, which is resistance and reactance of the primary winding. Hence the voltage at the primary circuit is equal to the induced EMF plus current flow through the primary winding multiplied by the primary impedance. And we've already showed that part of the primary current is supplying the no load losses, and the other part is responsible of the energy transferred from the primary to the secondary windings. Now, to eliminate any confusion, in equation 1b, an ideal transformer is assumed, so the no load component is neglected, and hence I1 dash equal to I1. The no load current is equal to the shunt admittance multiplied by the induced EMF at the primary winding, and we've already introduced that shunt admittance in terms of resistance and reactance. In parallel, we also introduced the secondary impedance Z2, and if we go back to the equivalent circuit in the previous slide, the voltage at the secondary winding terminals V2 equals to induced EMF minus the current flows through the secondary winding multiplied by the impedance of the secondary winding. If there is inductive load consists of resistance and reactance, then the impedance of that load would be ZL, and the voltage at the secondary winding would equal to the secondary winding current multiplied by that load as well. So if we take Laplace transform of the previously presented equations, rearranging them in terms of the applied voltage at the secondary as an output, we'll get the set of equations presented here. So if we really look to these set of equations, in equation 11a we are relating primary current and mutual inductance to the supply voltage, and in the second equation we are relating no load current, which is part of the primary current. The other part is I1 dash, which is related to the secondary current. In equation 11e, a relationship between the transformer output voltage, induced EMF in the secondary winding, and the current flow in the secondary circuit is presented. Now, since we are using transfer function blocks, we have to make sure that numerator and denominator of any transfer function presented has at least the same order. Now, to simulate a transformer, the parameters presented in table 1 are used. So the resistance and inductance in the primary and the secondary winding are presented, in addition to inductive load applied to the terminals of the secondary windings, to the terminals of the transformer itself. Now, as we mentioned earlier, three approaches have been used. The first one is to use transfer function blocks. So transfer function should represent the primary winding, the losses in the transformer, and the secondary winding impedance in addition to the applied load impedance. In the second approach, we are using blocks represents resistance and inductance in addition to an ideal transformer as shown in the equivalent circuit presented earlier. Alright, so in the third approach, we are using the built-in transformer block. Just need to connect the primary winding terminals to a power supply and the secondary winding terminals to a load. Now the signal obtained from the third approach will be compared to the first two models and hence validate the first and the second modeling approach. Now I've already started MATLAB. Okay, so we can submit Simulink and open a new window by either clicking Simulink or write Simulink in the command window. Let's go and bring the blocks we need to build the model. So I'm going to build the model first, and then I'm and then I'm going to explain how it works. So two scoop to show the current and the primary current and secondary voltage. I guess that's enough. Okay, so what do we have? We have a voltage source on an alternating current voltage source feeding the transformer model. When we subtract the input voltage from the electromotive force E1, we would get the multiplication of the primary current by the primary impedance. When we divide that quantity by the primary impedance, the result would be the primary current. Alright, so when we subtract I1 from I1 dash, the no load component can be found. We multiply the no load component by the shunt admittance to obtain the induced EMF in the primary winding E1, and when we multiply it by the turn ratio, the induced EMF in the secondary winding is presented. Now it's a little bit tricky here, but the main idea is to avoid using transfer function which has a numerator order higher than the denominator. So multiply the induced EMF in the secondary winding with this transfer function to find the secondary winding voltage, and simply divide the secondary winding voltage by the applied load to find the current in the secondary winding, which is transferred back to the primary winding by multiplying it by the turn ratio. Again, we are trying to extract the primary current and secondary voltage. Now let's go back to the command window and trying to define the parameters that are being used to run and simulate the model. Now some of those parameters have been taken from the demonstration model of power transformer exists in MATLAB. I'm going to show that in a minute. Okay, so we start with the primary impedance. Then the shunt admittance parameters. And then the secondary winding parameters. And finally, the load applied to the secondary winding terminals, which consist of a resistance and an inductance. this transformer operates on 60 Hz frequency. Now the demonstration model, I've been taking some of its parameters to simulate to model and simulate transformers. We can call that by writing power transformer in the command window, which is this one. This transformer is using three winding, a single phase 3 windings transformer. I'm relying on this model a bit more in the next video when I present single phase 3 windings transformer. Alright, okay, so we defined the parameters required, and then those parameters now exist in the workspace. The only thing we need to consider is to input those parameters in the signal generator, sine waves signal generator. So the frequency we defined was in hertz, and this block requires define the frequency in rad per second, so we need to multiply by 2 pi. I guess we need to fix this. Let's check the waveform. Okay, so this is the first model. Let's go and build the second one. Okay. And finally, the ideal transformer. I guess those components would be sufficient to build the model. this model is almost finished. We just need to define the parameters. So basically this is the primary impedance, the shunt admittance, and the ideal transformer. So we defined K as primary to secondary voltages, while in this ideal transformer block it defines secondary to primary voltages as the turn ratio or the winding ratio. Now the secondary windings impedance parameters have to be set, plus the inductive load, and the voltage source. It's already 60 Hz. So the next step is to compare the first model output to the second. Okay, so they seemed to be identical. Okay, so the yellow one is the first model, and the blue one is from the second model. If we remove one of them, if we remove the blue signal, okay. Alright, so let's go and build the third one. So we are using a linear transformer, which can represent two windings or three windings single phase transformer. And we do need our graphical user interface. Okay, so first things first, we are using two winding transformers. We're going to feed the parameters in real values. So again, I'm using the same parameters. And we just need to Okay. Okay, so it's either using the series RLC load, but in this case we have to calculate the active and reactive power, or we can use this RLC branch block, where you can simply define the inductance and resistance. So we'll omit this one, so delete this one. Basically, we need to compare the signal generated from the third model to the first and second models to validate that those two models work properly and can simulate two-winding single-phase transformers. One remark for the first model is that building the model in this way, we can find the current, secondary winding current in terms of the induced EMF in the secondary winding, and then find the voltage of the secondary windings using these two equations. In this case we have to use the derivative block, and I've seen a lot of discussion trying to avoid using derivative blocks. Alright, so let's go back to the model and check the results of the three models. Okay, so the three signals from the three different models seem to be identical. So the dark orange is coming from the third model, the blue one is coming from the second, and the yellow one is coming from the first model. So with this we conclude this video. These are the references cited early in this presentation, and thank you very much for watching.